Shall we? Okay. Okay, we're going to switch gears now and talk about emerging memory technologies. But what we talked about earlier is orthogonal to any memory technology. So whatever you use to implement main memory, you'll have the memory interference and quality of service problem. So it's so fundamental. I think this is also a fascinating topic. I think we're covering a lot of fascinating topics. There's no end to it in computer architecture. It's amazing. And there will be more. Believe me, it's going to come soon. I think today I was reading another AI chip startup coming up with a huge, some petaflops per second engine. I don't remember the name of it, but okay, it was called Grok, I think. If you search for GROQ, you'll find another machine learning accelerator. I just saw the news today somewhere, and they were advertising this with maybe the first petaflops engine that we have in a single chip today. Now, I don't know if that's true, and they don't have a lot of technical detail on it, but you can take a look. These things are happening today. Okay, and emerging memory technologies were, at least to replace main memory, was a dream even 5 years ago. But today we actually have this. I showed this as one of the exciting things that's happening in computer architecture today in the first lecture, right? Today we have the persistent memory, Optane persistent memory by Intel. You can buy it, you can plug it into your DIMM, and you can use it as persistent memory. But I will give you the story of it and history of it a little bit. Clearly, memory technology has played a very important role in the development of computers, right? DRAM, for example, was invented in 1965 by Bob Denard, and it's been the dominant memory technology for decades and decades and decades, and it's still the dominant technology for main memory today, right? It replaced the clunky core memories of 1960s or 1940s, 50s, right? But that sort of big revolution in memory technology has not happened in main memory for 50 years now, actually. The key question is, can that happen with some memory technologies, especially with the problems that we're facing with DRAM, right? We're pushing the technology so much that it's actually breaking, in a sense. Of course, we don't want it to break. We want to provide solutions to it, as we discussed in many lectures. But can we actually continue with this sort of technology, or should it be replaced somehow, or should it be augmented somehow? So that's what this lecture is about. And if you look at the broader space of memory technology, SRAM has been around for a long time, right? SRAM is a very powerful memory technology, very fast, unfortunately not very power efficient, and not very high density. As a result, it's not employed as part of main memory because of that. There are very few systems that employ SRAM as main memory. You can actually buy SRAM chips that you can attach to some processors. But that's not the common case, clearly, because you cannot afford a lot of SRAM. So if your data is relatively small, you can use SRAM as your main memory, but that's expensive. And on the other side, on the storage side, there are a lot of memory technologies also, right? Clearly, hard disks are an example. Tape is an example. Those are all memory technologies in the end. Hard disks are a more common example. They've been around for a long time. They operate based on different principles. But now they're increasingly being replaced with SSDs, especially in devices that require power efficiency like this. So SSDs are a technology that have replaced hard disks in many domains, right? I don't know why this is flickering again. If I figure out that, that'd be nice. But it's not going to happen, I think. So memory technology has changed a lot. But you can see that these movements in memory technology doesn't happen a lot or very often. And actually today, I'm not going to talk about some of these, but people are considering even other memory technologies, mainly for persistent storage, like long-term storage. For example, Microsoft is experimenting with glass-based storage. They really want to etch long-term data into glass. If you're interested, you can take a look at it. It's in the early stages, but I think that's a very promising technology going forward. Microsoft also is doing work on DNA storage. Can you actually store data in DNA for long term? Those technologies are also very interesting. It's very compact, clearly, right? DNA is extremely compact in terms of how much data it can store. Glass is also that way. Now, the upside of these are very durable long-term storage devices, although DNA is arguably very approximate. I think glass is a bit better in that sense. But their latencies in terms of read is very, very long. So they're very, very interesting technologies from a completely different perspective than we're going to talk about today. You cannot use those technologies as main memory. You cannot, I mean, it's even hard to use those technologies as your primary storage devices because SSDs are extremely fast compared to them. Reading the DNA can take seconds or minutes, or even longer, depending on how many errors you would like. Also depends on how big of a portion that you're going to read, right? It's a very sophisticated process in the end. So those technologies are very, very interesting, and they're also emerging, but they're really out of the scope of what we're going to cover today. We're going to focus on the high-performance technologies that can potentially replace DRAM. Or even maybe they can potentially replace disks. I think that replacing the disks with these technologies is easier. When I say disk, it's really SSDs. And they can potentially replace some of the L2, L3 caches. Okay, now we have a catastrophic failure. Somebody's hammering my computer probably. Who's doing that? Somebody here who doesn't want to continue the lecture? I should turn off my network. Okay. What I'm saying is some of these technologies have even the potential to replace actually SRAM, large SRAM memories that we have on chip today. For example, STT-MRAM is a very good candidate for potentially replacing L2 and L3 caches because the density it has is similar to SRAM, but it has characteristics that are also similar to SRAM in the end. But also it also has the ability to keep the data. I don't want to call it forever, but it's non-volatile essentially, whereas SRAM is volatile. So it can actually provide on-chip non-volatile storage if it replaces part of your SRAM, right, or all of your SRAM. Okay, so the focus is on high performance here. Okay, so basically if you look at DRAM, okay, let me do this. Because this was not working also. No, it's still not working, interesting. Okay. We're going to use it the old-fashioned way. Okay, that's not working also. Okay, that's not working. How about this? Okay, that's much better. Okay, so if you look at DRAM, well, there's flash also here, but essentially DRAM is charge-based memory. And whenever you have charge-based memory, and whenever you reduce the size of the charge storage unit, reliable sensing becomes difficult. You become subject to a lot of noise. Refresh is one example of that noise. It's leakage noise, let's say. Rowhammer disturbance effects are another example, and there are many, many other examples. Essentially, it becomes difficult to store charge, place charge, and control the charge. Essentially, charge escapes relatively quickly. In DRAM, it's a capacitor charge. In flash, it's the floating gate charge. And that's what we're going to attack with emerging memory technologies. And so far, what we've covered is to solve problems associated with it with using new memory architectures. Right? Remember this slide? I actually showed the previous slide also earlier. Can we actually overcome the shortcomings of a scale technology with more memory-centric system design by having more intelligent controllers, new memory architectures, new functions, new interfaces? And we didn't talk about data waste management, but we need to do, well, I guess we did talk about data waste management in terms of reducing latencies, right? And getting the refresh overhead. Basically, a lot of the refreshes are wasteful. You're getting rid of a lot of refreshes. And we talked about a lot of key issues to tackle. How do we enable reliability at low cost? How do we get high capacity? How do we reduce energy, latency, improve bandwidth, reducing waste, and enabling computation close to data? Now, a lot of these are also applicable to emerging memory technologies, actually. A lot of the ideas that we've discussed are really agnostic of DRAM, like computation close to data that happens in emerging memory technologies. If we have time, we'll talk about that. But reducing energy, latency, improving bandwidth, they're all applicable. So these, what we covered so far is important for DRAM, but by no means they're specific to DRAM. Keep that in mind. Any memory technology you can improve with the ideas that we've covered so far. And okay, I'll skip this one. Now we're going to focus more on the second direction. So this doesn't, even though we have two solution directions, this doesn't mean that they cannot be combined. Now we're going to talk about technologies that are not charge-based. These are resistive memory technologies. And it turns out these technologies are more scalable than DRAM. And on top of this, they're non-volatile. Essentially, when you plug out the power, they don't lose data. you don't need to refresh it. So one example of this is phase change memory. In phase change memory, you have multiple phases, and data is stored by changing the phase of the material. And you read data by detecting the material's resistance in a given phase. I'll give you a more concrete picture of this. But this is actually relatively old technology. I mentioned this was invented in 1960s. And it's actually used in rewritable CDs. And it turns out the phase of the material, let's say you have two phases, and these phases have two completely different resistances, so you can distinguish the phases by detecting the resistance of the phase. But these phases also have completely different optical reflexivities as well, so you can distinguish which phase the material in by shining light on the phase also. And rewritable CDs work with that operation. You basically shine light, and as a result you can distinguish which phase the material is in, and then you can distinguish between a 0 or 1. Unfortunately, that's a very slow reading process. Optical reading, in that manner at least, is very slow. As a result, rewritable CDs are clearly not a medium that you would use for main memory. Whereas reading this device by detecting the material resistance has become extremely fast in recent years. Especially Intel and IBM have done a lot of work in this area. They built a lot of different types of read devices that can operate reliably to detect the material's resistance, and that can operate really fast as well. And that work has enabled essentially the use of these devices as part of main memory. Okay, and at the same time, ITRS was projecting that DRAM scaling will be extremely difficult. They were saying that phase change memory is expected to scale to 9 nanometers. Now actually, this scaling has gone down to 3 nanometers or so. If I believe that's the current status, unless they reduced it even more. And as early as 2008, it was prototyped by IBM at 20 nanometer feature size. DRAM is actually currently around 20 nanometers, let's say. Actually, it reached 20 nanometers a couple of years ago, but this is 2008, right? And this is a manufacturing process that is not optimized at all, and they were able to do it in 20 nanometers. Whereas DRAM manufacturing has decades of history behind it, right? People have optimized that manufacturing for 50 years now. So it's very sophisticated. So this clearly shows that these technologies are easier to scale. And this is a very beautiful paper, actually, if you're interested in reading a very low-level paper on phase change memory. This paper by IBM Journal of Research and Development that was written in 2008 talked about the technology very, very nicely. It's a very low-level paper, that's why I'm not assigning it. But I would definitely recommend this paper to you. If you're interested in another low-level paper on phase change memory, there's another paper by Philip Wong from Stanford, who's done a lot of work on phase change memory also, on proceedings of the IEEE. I believe in 2010 it was published. That also talks about phase change memory. These are device-level papers. And phase change memory, because it can scale to smaller feature size, clearly it's expected to be denser than DRAM. So capacity is a big advantage of this. But on top of this, it's expected to be doubly denser than DRAM because you can also store multiple bits per cell. Essentially, you can divide the resistance range into finer grained pieces than just two. And you can encode multiple bits of data inside that single resistance range for a given cell. Just like flash technology today. You cannot do this in DRAM. Well, I guess you could do it in DRAM if you have a very, very good sense amplifier. But your sense amplifier needs to be extremely strong in that case. And that requires a huge sense amplifier in general. And that reduces your area significantly. Whereas it's easier to do in phase change memory. Okay. Of course, these sound good, but life is not as beautiful as it's written on the top of the slide. Emerging memory technologies have many shortcomings as well. And we'll talk about some of these shortcomings. The key question that we're going to try to answer in this lecture, I won't have answers, but we will actually examine the question. Can we somehow enable these technologies to replace or augment or maybe even surpass DRAM? And these are all possible depending on what aspects of the technology you use, right? For example, we can surpass DRAM by exploiting the persistence of the memory technology. DRAM clearly cannot retain data across power cycles, whereas these memories are persistent and non-volatile, meaning that you can store persistent data in them, and you don't need to do another transfer between DRAM and disk. So as a result, you can surpass DRAM. In terms of capacity, you can surpass DRAM also potentially, but in terms of latency and energy, we will see that they have shortcomings. And it's going to be difficult to completely replace DRAM because of that reason. Okay, we're going to cover some of these works over here. So what's the fundamental difference? Basically, if you look at charge-based memories, you write data into a storage device by capturing some charge, and you read data by detecting some sort of voltage, essentially. Whereas resistive memory technologies, of which there are several examples, phase change memory is one example, we will talk a lot about it. STT-MRAM, spin transfer torque, magnetic memory, it's a sort of magnetic memory, we will talk briefly about it. Memristors, it's more resistive memory, they operate on different principles, we will not talk a lot about it, but you can find literature on it also. Essentially, they're all resistive. They store data in terms of resistance. Basically, they write data by pulsing some current into a particular storage device, and that changes the resistance state of the device. And you read the data by detecting that resistance state, essentially. That's the idea. And you can go into more detail of how this exactly works underneath. We're not going to do that a lot, except for a couple of slides. So let's talk about these technologies at a high level, basically. If you look at phase change memory, you basically, these operate on different principles, also the different materials as well. You inject current, in phase change memory, you inject current to change the material phase. And this current is injected at very high temperatures, basically. And the resistance is determined by the phase, in this case. STT-MRAM is also very promising. You inject current to change the polarity of a magnet, in this case, which is different from material phase. You basically make the magnet parallel or anti-parallel compared to a reference magnet. That's the idea at the high level again. And the resistance is really determined by the polarity of the magnet, whether it's parallel or anti-parallel to some reference. Memristors, RRAM or VRAM, these have slight differences in terms of their technology, and clearly there's a naming issue over here also, as you can see. But essentially you inject current to change some sort of atomic structure of the storage unit, and resistance is determined by some sort of distance between atoms. So how do you determine it becomes interesting, but we're not going to talk a lot about that over here. And all of these are interesting, and at the time when I prepared the slide, I think this is about 2008 or so maybe, all of these were contending with each other. And there are also some other technologies like conductive bridging RAM, but I'm not going to talk about those. Those are also interesting, but I think they're not as close as these at this point. But at that point, there was a big competition between them, and people were actually trying to, they're still trying to get some of these devices into the field. I believe phase change memory, even at that time, you believe that phase change memory was closer to production, and I believe it's already in production right now, as we will discuss in a little bit. So we're going to focus more on phase change memory, because at the time, and also at this point in time, I think it's the closest to replacing DRAM. Although I think STT-MRAM and memristors can potentially disrupt if people can find ways of manufacturing them relatively easily. Okay, so what is phase change memory? Essentially, you have some sort of phase change material, and one example of this is some sort of glass, low-level chalcogenide glass, that exists in two states. One state is amorphous, the other state is crystalline. And as I already said, these two states have opposite reflexivities and opposite resistivities. And there's a huge range in the reflexivity and resistivity, and that enables reliable reading of the different, reliable identification of the different states. So you can see one example of this device. So you can see the bit line and the access word line, and a heater and chalcogenide glass over there. Okay. And once you abstract it, it kind of looks like a DRAM cell in the end, right? Once you abstract any memory technology, you have a storage device and an access device. Which depends on the abstraction level you're looking at. But if you go inside, the device may be very different. Okay, you can encode high resistance with some value and low resistance with some other value clearly. And the cell can be switched between states reliably and quickly. And that's the idea. Okay, let's go into a little bit more. Essentially, how does this work? In order to write to the cell, you need to change the phase by injecting some sort of current. And this is actually not the easy process, this is a hard process. For example, if you want to set the cell, you need to supply sustained current to keep the cell above some crystallization temperature. And this gives you a picture, for example. You need to essentially sustain the current for some amount of time, and that amount of time is like much longer than DRAM. Let's say 10 to 12x longer. And I believe in existing 3T X-point devices, it's even longer. I don't want to say any numbers, but there are some publications out there that claim some numbers. You can read those if you're interested in 3DX point. But it's much longer than DRAM, basically. That's the takeaway. And you need to sustain it for some time at high temperatures, as you can see. To reset, actually, you need to heat the cell even to higher temperatures, above some melting temperatures, and then quench the cell relatively quickly. So set and reset, you basically do 0 or 1, essentially. And reading is essentially a mechanism that detects the phase via detecting the material resistance. And that there's a device to do it. We're not going to go into detail. You can read that IBM Journal of Research and Development paper for examples of those devices in 2008. Or the Philip Wong paper from 2010. And there are a bunch of other papers that came about that talk about devices. But that's not our subject, basically. We are assuming that there's a reliable device. Just like in the DRAM, we have a reliable device to get the data out, right? Sense amplifiers. We didn't go into the details of sense amplifiers clearly. Okay, so this is one example picture. Basically, this is a set state. You have low resistance over here. To get to this, you need to supply some large current, clearly. And this is a reset state. Essentially, you have very high resistance state over here. Right? And it's kind of, usually you look at this mushroom cloud. People who work on patient engineering, we talk about the mushroom cloud. And if you ever wonder about the mushroom cloud, it looks like this, basically. Anyway, okay, so what is this? Essentially, this is, you can see the resistance ranges over here also. And this is important, actually, this on and off range, it's also called. If this resistance range was very small, then the noise margin essentially is very low, and as a result, detecting the different states will not be very easy. The high resistance range enables the detecting of many states, and the high resistance range also enables chopping this resistance range to finer values so that you can store many bits per cell. So that's very important. So whenever you have a new memory technology, it's really important to look at this difference between on-off resistances or on-off differences between different states. If this range is small, then you'll have a lot of problems with your technology in the end. Okay, so let's take an architectural perspective and let's talk about what are the advantages of this from an architectural perspective. Right. First of all, it scales better than DRAM. It scales better than flash memory. Actually, flash memory, as I mentioned earlier, this slide was created much earlier than 3D NAND introduction. Basically, flash memory manufacturers figured out a way of scaling flash memory by going three-dimensional. Right? And as a result, I think flash memory has gained some time in terms of scaling better. But over time, in terms of the cell size itself, scaling characteristics of in terms of an individual cell itself, the scaling characteristics of phase change memory is much better than flash memory, essentially. If you reduce the size of a cell in flash memory, you're bound by reducing the charge to levels that are very difficult to control. Whereas if you reduce the size of a PCM cell, your resistance ranges still remain nice, essentially. That's the idea. Okay, you can read this paper for more detail in terms of scaling properties, essentially. It can. I also said that it can be denser than DRAM, and even as early as 2008, people had prototypes of 2 bits per cell. And you can see, you can date my slide based on this, right? 4 bits per cell by 2012. Clearly, we're beyond 2012 right now. And people have actually looked at PCM cells that can store many bits per cell, 8 bits per cell. And I believe they're working on 16 bits per cell. That means you divide the resistance range into 16, right? Okay. It's non-volatile. It can retain data for clearly much longer than DRAM, right? Although there are issues related to this also. You may need to refresh this also. We will talk about that very briefly. Well, I guess here we'll talk about that. There's no refresh needed, ideally, and it leads to low idle power because your leakage is very low. This no refresh needed is true, but it turns out, just like charge leaks, resistance also drifts. So your resistance values over time drift slowly, especially as the cell gets older and older. Older meaning you write to the cell many, many times. At that point in time, your resistance drift becomes larger. So you need to provide some sort of refresh, meaning you need to rewrite the data into the cell. But the time scales at which you need to do a refresh is orders of magnitude larger than the time scales that you need to do a refresh in DRAM. It's not 64 milliseconds. It's much, much higher. That's true for flash also. We briefly discussed refresh in terms of flash, right? Flash is a non-volatile memory technology. Even though it's charge-based, the floating gate can keep the charge across power cycles. But charge leaks out of the floating gate, especially when the cell gets old, meaning you've written to the cell many, many times, it's degraded a lot, and now you need to really start refreshing it. But normally you start refreshing it every 3 months, let's say. And then as the cell gets older, you increase your refresh rate maybe every month. As the cell gets even older, you increase your refresh rate to every week, let's say. And as the cell gets older, it becomes every 3 days and maybe every 3 hours at some point, right? So that's the scale we're talking about here. And in this case, the scale is even, well, it's actually not clear what the scale is exactly over here because there's not good enough data in the field related to this. But it's similar to flash as opposed to DRAM. Okay, so low idle power is important because the leakage is actually, charge leakage is much faster because it's charge-based memory. Here we're based on resistance. So the static power is very, very low in these sort of memories. So you gain a lot of power reduction because you get rid of refresh, and you remember refresh was really the scaling limit of DRAM, and we kind of got rid of it at this point. And the static power is also gone for practical purposes, let's say. Clearly it's not gone, there's always static power, but compared to DRAM it's gone. So there's going to be a big energy advantage of these technologies also. Look, you have a question? Yes.
In DRAM mostly because in order to get more number of bits but the amount we are paying, we are trying to shrinking it. So is it like this PCM is cheaper compared to the DRAM? Is it
when, cheaper in terms of number of cost per bit? Yeah. So in terms of cost per bit, over time it's expected to become cheaper. Yes. So if you do the scaling calculations, if you invest the same amount of money into manufacturing, this is definitely going to be cheaper. No question about that. But DRAM is currently at a point where there was a lot of investment that is done in the manufacturing technology. And the manufacturing technology is so precise and so optimized that its cost per bit is relatively low right now. Does that make sense? But over time, this is expected to be much better because scaling, essentially you can cram more bits in a given area. Okay. So essentially, as we discussed, resistance is what really encodes the value. You basically have a cell's resistance range for each cell, and you basically have a cutoff, the threshold resistance, and everything below the threshold is encoded as a 1, everything above the threshold is encoded as a 0, right? So it's similar to DRAM, except in DRAM it's really about voltage, right? Okay, but the voltage range is actually very, very low in DRAM. Okay, if you look at the multi-level cell PCM, essentially can store more than 1 bit per cell. It can increase density by 2 to 4x, and actually more right now. But also, when you go to multi-level cell, it's not for free, essentially. You gain capacity clearly by chopping up your resistance range into finer grain, as you can see over here. In this case, 4, and then now you can. Now you can encode this resistance range as 1, 1, this resistance range 1, 0, 0, 1, and 0, 0. But this clearly comes at a cost because now you need to be able to read, right? And write also multiple bits. And that takes longer in this case. For example, if you want to be able to read this, you really need to supply one resistance over here. That's one way of reading. It's usually a two-step reading. You first supply this resistance, and then you figure out the value somewhere over here or over here. It's like binary search, right? And then once you figure out whether the value is on the left or on the right, you supply another reference resistance, and then read the least significant bit. So you first read the most significant bit, which is 0 on the right and 1 on the left, and then you read the least significant bit. So that takes longer. Essentially, it takes longer to get to both bits, and it takes more effort, more energy to get to both bits. So there's a trade-off between capacity and latency in multi-level cell PCM. That's true for flash also. If you buy flash, you can make it low latency by reducing the capacity. Right? And if you remember, when we talked about latency, I said this is a very fundamental trade-off between capacity and latency. It's it's hard to break that trade-off. It's manifesting itself in a different way right now. Right? Even within the storage in a single cell, you can cram more bits, but to get to those bits, you need to expend more latency and energy. Very fundamental trade-off. It's very hard to break. Yes?
Better than two cells, different cells?
Better in what sense? Not necessarily. Yeah. This could be longer potentially. Yeah. It depends on where you put those two different cells. Right? If they're in two different banks, they don't affect each other's latency. Okay. So there are also other issues in MLC, multi-level cell PCM. So if you go back over here, your noise margin is a lot higher here, right? If you store a single bit, single level cell. This is also called SLC PCM. SLC flash has the same thing, except in flash it's the voltage range over here. And if you encode more bits within the same resistance range, now your margins are much lower, right? Meaning, for some reason, if there is noise in your system, this resistance may drift to the right more easily. So you can get bit flipped more easily this way. Make sense? So reliability of multi-level cell PCM is lower by nature. That's true for multi-level cell flash also. Reliability is fundamentally lower. That's another trade-off. And if you've been seeing these trade-offs, right? It's another fundamental trade-off. Your capacity becomes higher, your reliability becomes lower. It doesn't require your cell to scale smaller. If you cram more bits in a single cell, you have the same trade-off in the end. Okay, basically you have less margin between the values, so you need more precise sensing and modification of cell contents, and this requires higher latency and energy. And these are some numbers empirically obtained from devices, basically 2x for reads and 4x for writes. That's a lot, right? Okay, but of course you can optimize it. Okay, so let's take a look at this a little bit more architectural. So basically when we first started looking at this, I was at Microsoft Research and we were really fascinated by this technology and we really wanted to understand the implications of this technology in terms of architecture. Can we somehow get rid of DRAM basically? That's the question we had. So what we did was we really, at that point of course we didn't have PCM chips in our hands. Very few places had PCM chips in their hands. And even if they had PCM chips in their hands, they were usually as big as 512 bits or so. Clearly you cannot do the study in a real system, right? You cannot take a 512 bit chip and run your application on it. Not so easy. That's the difficulty of dealing with emerging memory technologies. If you're an architect, if you're thinking about like 20 years down the road, you need to anticipate the technology and you also need to do the experiments. But you cannot have the technology to do the experiments, so you need to project in the end. How do you project? Basically, you need to look down, in a sense. We discussed the roles of an architect. You need to look down and figure out what's going on in the technology layer. And we did survey a lot of prototypes that people at the device level built in essentially device conferences, and some of them are also in circuits conferences. And there were some prototypes at that time. And I will show you a table that summarizes the prototypes. And these prototypes all disagree with each other, it turns out. There's some agreement, but a lot of them have disagreement, and a lot of them have information that we're looking for, but they don't provide that information for whatever reason. Either they don't have it, or they cannot provide it for some reason. So we surveyed prototypes from 6 years over here, and we tried to derive parameters for phase change memory for a feature size of 90 nanometers. There's also another thing with these prototypes. Some of these prototypes are relatively large, because some of them are academic. Even if they're company prototypes, some of them are relatively large, because they don't want to use their cutting-edge production technologies to actually manufacture these devices to begin with. And they may not have the cutting-edge manufacturing technologies for this sort of device. Okay, so if you want to do that study, essentially you study a bunch of papers, works that publish data on these devices, and you look at different parameters. And you can see some of these are manufactured in 2003, 2008. You can see the process technology. It's about 90, the best one at that time. You can see the array sizes. Actually, some of them are pretty large, but these are not full chips. These are actually just arrays that are manufactured, so you cannot actually access them in some way, easily at least. And you can see different materials, different cell sizes. You can see different devices for access. You can see different read times. For example, this is 70 nanoseconds. So the read times actually are good. according to a lot of these. You can see the read currents, read voltages, a bunch of different stuff. One thing to see over here is energies over here. There's write endurance over here. That's important. This basically says how many times you can write to a cell before the cell goes bad. On average, at least. You can see the numbers are relatively small. Some of them are 10 to the 4. The best one is 10 to the 9 over here. And 10 to the 9 is not a lot. Right? 10 to the 9 is, how much? It's a billion, right? 1 billion basically. And you can easily do 1 billion writes to main memory very quickly very quickly. Okay, so we have problems with the technology, as you can see over here. And you can see that there are a lot of points that are not provided. So this one's a good one. This one is one of the Micron chips that was manufactured in 2004, and they provided pretty much all of the numbers over here. I think this work was done by the group that's in Milano, which is close to here. Okay, so basically let's take a step back and let's look at the architectural perspective. Right? If you look at the latency of this technology, if you look at all of the data, the technology is placed very close to DRAM. It's not as good as DRAM, but it's reasonably close to DRAM that we can do something good with it, hopefully. It's very far away from flash, as you can see. It's much better than flash. And I like this picture because it shows you where different technologies are. Okay, so basically let's give some numbers. Read latency, according to our calculations, we said it's going to be about 4x of DRAM. But it's going to be 3 orders of magnitude better than NAND flash, which is a really good thing. Write latency is 12x of DRAM. Could potentially be slightly smaller than flash. Write bandwidth is less than DRAM, similar to flash. So bandwidth is not that great. Bandwidth is limited by power, actually. Whenever you need to actually write to a cell, you need to heat it to very high temperatures. And those high temperatures are hundreds of degrees, which is not good. Which means that you cannot sustain a lot of writes at the same time. That's why your write bandwidth is not as good as DRAM here. Of course, people have developed the technology over time a lot, and it's become better. I believe 3DX Point does a better job than what was reported 10 years ago. But they don't expose a lot about the system, so we don't know. So energy is actually somewhat problematic. Read energy is maybe okay, it's 2x of DRAM, but write energy, because of that huge current that you need to inject, it's more than 40 times that of DRAM. Not so good. So you don't want to write to this memory, essentially. And we will discuss that. And there's another reason why you should not write to this memory, which is endurance, right? So these writes induce phase change at very high temperatures. And because of that of those high temperatures, contacts degrade because of thermal expansion and contraction. And at some point, if you do enough writes to a cell, your contacts degrade beyond repair. As a result, you cannot write to the cell or read from the cell. And that's the endurance problem. Flash has a similar endurance problem, but it's not because of the current. It's really because as you keep writing, you're unable to actually do tunneling inside the flash device. If you talk about flash, we'll talk about that. But flash endurance is actually much worse. As you can see, in DRAM, there are not good numbers over here, but DRAM is a technology that's claimed to have no endurance problems. You can keep writing to memory forever. I don't believe that's true, because I don't think there's anyone who has tried writing to the memory forever. Maybe you can try during your lifetime. Start writing to your memory today. Keep doing it for, 60 years, and we'll see if you can still write to that location. That's a long-term study that's not easy to do, I think. But still, for all practical purposes, it doesn't have an endurance problem. NAND flash clearly has an endurance problem. If you have the flash memory lecture, you will see that for triple-level cell flash devices, these are devices that can store 8 bits per cell. The write endurance is only 100 times. Basically, you can write only 100 times to a single cell. Okay, if you improve the technology, maybe 300 times. Not so good. For multi-level cell devices, this is about 3,000 times, which is very small also, right? Basically, you write to a cell only 3,000 times. After that, you cannot write to the cell. But flash memory is not used as main memory, so it doesn't get exposed to writes a lot. Whereas if you want to use a technology as main memory, it is better have good write endurance, or you have to solve the problem in some other way, because you're going to write to this memory at some point, right? Okay, so this is not good. Cell size is actually better than DRAM, even though at the time we looked at this, it was bigger than DRAM. We expected that it will scale with feature size and multi-level cells, so we didn't think this was a problem in the end. The cell size can be made much smaller than DRAM in the end. Okay. We don't talk about reliability over here, but well, this is it's an example of reliability, but there are other reliability issues clearly that we're not going to cover, like refresh. Well, there are other reliability issues. Let me give you an example. Which I already gave you the example of what is this called? Not refresh, but resistance drift. Yes, that's the cause of the refresh. Clear. Refresh is the solution to the problem. Resistance drift is one reliability problem. There's also write disturbance that happens in these devices. Whenever you write to a cell, some other cell gets affected. That's actually a problem. A lot of phase change memory controllers need to solve this problem. There's read disturbance, not as bad as write disturbance in a lot of these devices and current technologies. Read disturbance is essentially similar to row hammer, right? If you keep reading from a location, some other locations get disturbed. So phase change memory controllers need to deal with all of those problems. And as a result, if you get a 3DX point memory, there's a controller associated with it, and that needs to deal with those problems. Okay, so let's take a step back. Basically, if we summarize the pros and cons of phase change memory over DRAM, the pros are very promising. Essentially, we have better technology scaling, so we get better capacity and better cost over time. Even though at the points we examined in 2007, that was not the case. Clearly, the capacity was 64 megabit, and the cost was much, much higher than DRAM. But if you project out to 20 years, and if the technology is going well, then there's no question that this is going to be a much lower cost technology than DRAM. It's non-volatile, so you can actually exploit the persistent data by putting on it, by manipulating persistent data directly in memory. We're going to talk about that hopefully. And it has low idle power. It has no refresh, so there's a power advantage of this. But of course, cons are not so great as well, right? The higher latencies, read latencies are 4x higher. That's not very good. 4x is very hard to tolerate, right? We're going to talk about prefetching next week. Prefetching tries to tolerate DRAM latencies. Now you're increasing the latencies by 4x. It's going to be even harder to tolerate. Write latencies, 15x. Write latencies are not on the critical path, but if you make them 15x, they may become the critical path at some point, right? Not so good. Read energy, 2x. Not good. Whenever you're reading, you're wasting energy. And write energy is 50x, basically, let's say. So that's also not good. And we already discussed the endurance. And reliability issues we're not going to cover. Essentially, this is challenging. Essentially, if you want to replace DRAM with phase change memory, you need to somehow mitigate these reds and exploit the greens, of course. And you need to find the right way to place phase change memory in the system. And when we first started thinking about this, we had this picture in mind. This is a picture from our first presentations. How should we organize this phase change memory based main memory? And this was the existing systems. And we thought that over time, you would transition to a hybrid memory system. And over a longer time period, phase change memory technology will evolve and it will become much better. As a result, you can replace DRAM entirely with phase change memory. So we were aggressive. We skipped the step and we wanted to look at this step in 2007. But we're going to get back to this hybrid, because hybrid is really a solution that could be a bridging solution, or maybe it's a forever solution if this technology never becomes as good as DRAM, right? So we're going to talk about this. If you have a hybrid technology, then the question is, how do you partition and migrate data between PCM and DRAM so that you can take advantage of both of the technologies, right? But let's now take a look at this one. We were, as I said, we were more aggressive, and we wanted to examine this and the implications of this on the system. And can we actually make this as good as this, or better than this? Now the question becomes, how do you redesign the memory as well as the entire hierarchy to overcome the shortcomings of phase change memory? Now in our work, we didn't redesign the entire hierarchy. We actually redesigned the phase change memory chips, and I'll show you some results related to it. And those are results from this paper, essentially. And these are the assumptions that are made in the paper. Density is not as important. We didn't examine the density implications. So we actually disadvantaged the new technology quite a bit. The study we did actually assumes that you have the same capacity. You have DRAM and PCM. Existing systems have DRAM. You're going to replace DRAM with PCM, and PCM will have the same capacity. So you don't have any capacity advantage by moving to a new technology. I think that really is a pessimistic view of a new technology. I'll show you some results from some other paper that took the more optimistic view. And we will see that the results will be much better. So if you take the pessimistic view, capacity equivalent view of this new technology, now you expose all of the downsides of the technology, right? The latencies are higher, as you can see, endurance is a problem, and energy is higher. Now what happens, now you can do simulations, right? You can take your simulator, you can actually use Ramulator for this purpose that you're working with now, not at that time. Currently you have the luxury of using Ramulator if you like it. Maybe you'll like it so much that you'll use it forever. I'm joking. I think Ramulator is not written in the best way, but that's fine. You can use the C# version, by the way. There's a C# version also. I like the C# version better. Because when we first started doing memory studies, we started with C#, because I was at Microsoft Research, right? Microsoft was big on C#. And my collaborator said, I don't know C++, or I don't know C, let's use C#. And I said, okay, sure, why not? Actually, C# is not bad, I think. It's very easy to program, but the performance is not the greatest. Because I think the performance has improved a lot over time, of course, by improvements to the .NET infrastructure. But anyway, that's digression. So basically you simulate, right? You can simulate what is the implications of this technology. And that's exactly what we did. Basically, we can simulate existing systems with DRAM, and then you can simulate what happens if you replace DRAM with phase-change memory and with some system assumptions. Right? So at that time we assumed the 4-core, 4 megabyte L2 system. And we assume that phase-change memory is organized exactly the same way as DRAM. You have the same row buffers, same banks, same peripherals. Basically, we're not changing anything. The assumption is that you're basically taking a single DRAM cell and replacing it with every single DRAM cell with a phase-change memory cell with appropriate properties that we showed in the previous slide. If you do that, and if you run some workloads, benchmarks, these are some benchmarks that are scientific benchmarks that are somewhat memory intensive. Some of them are more memory intensive than others. This is what you get, basically. Compared to a DRAM-based system, your performance degrades by 60%. Not so good. Compared to a DRAM-based system, your energy increases by 120%. Not so good. And your memory dies after 500 hours. It goes away because you have an endurance problem. And you're exposing every single write from your L2 cache into your main memory. Not so good. Basically, it's not a viable technology, right? If you don't do something about it. And that's the conclusion. And you can see that this is the years until which you can use your memory. And that's very small number, 0.02 years. Right? Some of the workloads actually consume your memory very quickly. Of course, it's not all of your memory, but we assume that there is a limit as to, I think it was 10%. Okay. So basically we said that, okay, we want to change the memory a little bit. And we basically did the optimization of the phase-change memory chips in this case. And if you look at this technology, if you want to make it work, the realization is that you don't want to write to it. You want to minimize the number of writes as much as possible. So how do you do it? We're going to later see some system level techniques, but we actually designed some chip level techniques inside the phase-change memory chip. The first realization is that in DRAM, you have sense amplifiers as wide as the row, right? And in DRAM, you need that. Because whenever you read a row, you destroy the values in the row, and you have to sense everything, and you have to restore everything. That's why you need a sense amplifier for every cell in the row. In phase-change memory, you don't need that. You're not really destroying the data when you read it. This is non-volatile, remember? You're just detecting the resistance. So you can read only a piece of it. You don't need to, you may still organize the memory in terms of rows, because that has some other benefits, right, in terms of how you lay out your memory. And also address benefits. But you don't need to actually have a sense amplifier for every single cell in your row. So here the row size may be 2 kilobytes. Here the row size can be 64 bytes, right? If you want to read an entire cache line. And that's exactly what we did. We basically made the rows narrower, and we had many rows that can potentially be cached. So we basically converted these sense amplifiers to sense amplifiers, smaller sense amplifiers, plus some buffers that consume equal amount of space. So we basically don't want to change capacity. We're looking at a capacity equivalent system. And the capacity of this is equivalent to the capacity of this in the end. But now you can manage this buffer, right? This buffer can be managed as a cache, and you can actually absorb a lot of the writes. That's the idea. Whereas here, you may not be able to absorb a lot of the writes if they go to different rows. Here, you can absorb a lot of the writes that go to stuff in the buffer that may be from different rows. Okay, so this optimization leads to better endurance, better latency, and better energy because you can actually service some of the reads faster as well this way. So this is a good optimization for patient memory. But you cannot do this in DRAM. You cannot reduce the size of the sense amplifier in DRAM because the technology is destructive in terms of reads. Okay, so that's one idea. The other idea that we had, and this is actually, I believe actually both of these ideas are employed in existing PCM chips. This is also employed, but basically the idea is whenever you're writing data into a phase change memory chip, you don't need to write the entire row. You don't need to write the entire cache block. You just need to write whatever changes, whatever is different from what you read. Of course, to be able to do that, you need to keep some metadata in terms of what is different. And we looked at it in terms of cache block and word granularity. But you could actually do it at an even smaller bit granularity. In fact, there were some prototype chips that were designed by Samsung that looked at the bit granularity. What they did was, whenever they were writing data, they only wrote the bits that changed. But of course, you need some overhead. You need to have add some overhead to the chips to be able to do that. So clearly, doing this reduces some unnecessary wear out. Okay, now if you do this, these are the results that you get. They look much better. The performance degradation is only 20% now compared to DRAM. Energy is on par with DRAM. Take this with a grain of salt. I don't believe these results. Energy models are actually very hard to get correct, especially even with DRAM, even with existing technologies. Energy modeling is very hard. But now we're modeling energy for an emerging memory technology that we don't know enough about. Right? I believe it's not equal. It's probably worse than DRAM, but it's better than the 2.2x that I showed you earlier in the end. And now the average lifetime is much better than $500, 5.6 years. So it's better, but it's not as good as DRAM, right? Your DRAM normally doesn't die after 5.6 years today. I think I can attest to that. Maybe I cannot attest to 60 years, but 5.6 years, probably that's true. But this is average, so keep that in mind. Average is not a good measure for a lifetime in general, because the worst case is much worse. Okay, so the results look good, and we thought that scaling actually improves energy, endurance, and density. So the future of the technology is bright. But of course, there are caveats here. One caveat is worst case lifetime is much shorter. You can see that some applications, this is now years over here, and you can see that some applications consume your memory within less than a year. Not so good. And you can see that these are different granularities of writing to memory. And that granularity makes a huge difference. If you do cache block granularity versus word granularity, if you do word granularity, your endurance increases significantly. Okay, so worst case lifetime is, there's no guarantee essentially on worst case lifetime, which is not so good. In fact, one can construct an attack that can destroy your memory. You're running your application and some other application gets scheduled on your cell phone. It basically keeps writing to your phase change memory and your memory goes away. Not so good, right? It's possible if you don't have any protections against this. And later work actually looked at protections against this. I think this is important to fix. There's a second caveat. Even though the average performance degradation is relatively low, 20%, some applications lose performance a lot. You can see up to 60%, for example. And these are not necessarily the most memory-intensive applications. There are even more memory-intensive applications that you could run on these systems. So all of these results are somewhat bleak in that sense. So they're much better than before, but not so great also. And also energy. Right? Energy is also worse than existing systems in some applications. And finally, this is something that the jury is still out for. Basically, maybe we use optimistic parameters for phase change memory. Even though our parameters, compared to the other papers that we're going to see, one of the other papers, our parameters were more pessimistic than some of the other papers that were published concurrently. I believe the parameters may still be optimistic. Like Intel 3DX Point, I think their parameters are worse than what we have, I believe. But of course, they're going to improve in terms of technology also. But it will take some time for the technology to mature. Okay, so with these caveats, the takeaway is that, is this technology still good to replace DRAM? I think it is. I think our conclusion in this paper is, yes, over time the technology will improve. Even though these numbers do not look great, they're not bad also. Right. And of course, if you actually include capacity in these, if you get rid of the requirement that these are ISO capacity, if you actually look at a future point where the capacity of phase change memory is much higher than DRAM, you get other benefits, right? So that's a comparison point that I'm going to show in a little bit. Okay, so I think this is going to be your required reading, although I've covered a lot of it. And this is the paper. And later we were invited to write another paper, and we talked about some other issues related to the future of main memory. So this is, as I said, we started this in 2007. And it's always good to believe in the technology a little bit and do the research. And I always believe in the technology. People are always asking me, when will phase change memory happen? When will phase change memory happen? I said, I don't know. But it will happen someday. Or something like it will happen if it doesn't happen. And it's in the end very good to see things like this happening, right? So you have this idea in 2007 or so, and you think about it, you do a lot of research on it, potentially. And of course, somebody needs to do very hard work to make it happen. And I think this has happened, as I said, this year in 2019. Now you can buy this. And you can see that this is 128 gigabytes. It's not 64 megabits that we were dealing with in 2007 or so. So that's good. I think believing in the technology is a good thing in general. Especially if you have problems with technology, or if some technology looks promising, it's always good to invest in that. And if you don't make it happen, you lose some money, fine. But maybe you learn a lot while losing some money. And usually you don't lose somebody else's money. You don't lose your own money, you lose somebody else's money, right? Somebody else is willing to invest in it. And I believe they're investing in much worse technologies than something that fundamentally improves things today. Which is a bit sad also. There's a lot of money that's wasted in the world that's invested in stuff that's not so interesting. Whereas there are a lot of important problems to be solved if you invest in something really fundamental. Right? But sometimes people are very much driven by making more money, that they don't invest in the right directions. But I think this was a good investment. And I think this is going to become much more important and interesting into the future. We will see terabytes and terabytes, hopefully soon. And again, this is called 3D X-point, but I think a lot of the evidence in terms of the academic trail and presentation suggests that this is based on some sort of phase change memory technology. Okay, so this is not the only technology. Clearly there are other technologies, and I think STT-MRAM is also very interesting. I gave you the basic idea. Let me give you the pictorial description of it. In this case, essentially you use a magnet to store data. It's a fundamentally different technology. You have this magnetic tunnel junction device. You can see that over here. It kind of looks like this. You basically have two magnets. You have a free layer and a reference layer, and there's a barrier between them. Reference layer has some fixed magnetic orientation, and free layer can be modified, changed in terms of its magnetic orientation. And the magnetic orientation of this free layer with respect to the reference layer determines the logical state of the device. You can have high resistance versus low resistance if you're parallel versus anti-parallel to the reference layer. And there are many different implementations of it that we're not going to go into. Again, there are very interesting papers related to it that are some of them are referenced by this work over here. Essentially, when you write to this device, you need to push large enough current through this magnetic tunnel junction so that you can change the orientation of the free layer. So current is still a problem over here, but it's not as bad as phase change memory. You just need to change the magnetic orientation, which is much simpler than actually heating the device to hundreds of degrees Celsius. So in that sense, this is much more viable. But the technology, as we will see, has some shortcomings. And reading is also simple. Basically, people have built read devices that are actually very fast. In terms of reading, this is actually very close to the DRAM. You can actually make it as fast as the SRAM today. But it turns out this magnetic tunnel junction device is not as, its current state of the technology is very large. I mean, it's not as large as this, of course, but it's much larger than a DRAM cell. The size of it is, let's say, 60x of a DRAM cell today. So for it to scale to something smaller than a DRAM cell, it will take a lot of time. Whereas phase change memory size was already, at least theoretically, was smaller than DRAM, and even practically with some devices smaller than DRAM. So scaling was much better over there. Here it will take a lot of time, I think, to scale this to something smaller than DRAM. Here, I think, if compared to an SRAM cell, this is comparable, actually. So that's why this technology can potentially replace SRAM. And a lot of the technology is compatible with CMOS as well. So you can actually put it on a chip today. And people are experimenting with that right now. But of course, we were interested in main memory, comparing it to DRAM. Let's take a look at the pros. Pros of STT-MRAM over DRAM are very similar to pros of phase change memory over DRAM. Basically, a better technology scaling, non-volatility, low idle power, no refresh. Sounds great. But the cons of STT-MRAM are actually much better than phase change memory. That's why this technology is very interesting. In fact, for a long amount of time, actually, some people said this is the best technology ever. When somebody tries to sell you something as the best technology ever, that's good at everything, that's green at everything, don't believe them. There's no such technology, I think. All of them provide trade-offs. And people quickly realize that STT-MRAM is not the best technology also. But actually, its cons are actually not bad. Basically, you get higher write latency than DRAM, higher write energy, but read latency and read energy are actually good. It can be comparable to DRAM, and it can be comparable to SRAM actually. You can optimize it. Unfortunately, this con is bad right now. You get very poor density currently because of the cell size today. And we need to figure out how to reduce the cell size. And there are reliability issues just like any other memory technology. We're not going to talk about this, but there are, for example, reliability issues in terms of write disturbance also over here. And sometimes you get write errors or read errors. If you don't actually push the current in a nice way, you may not be able to change the magnetic orientation of the free layer. As a result, you get write errors, right? You may not be able to write the data correctly into the device. And those need to be solved somehow. Now, another level of freedom that's interesting in these devices is basically these are non-volatile. But you can make this device more volatile. How do you do it? Basically, by reducing the size of this magnetic tunnel junction device, you get rid of some of the non-volatility, but you can reduce the write latency and energy that way. Because the magnets are smaller, and as a result, you need to push a smaller amount of current to change the orientation. And as a result, you get lower write latencies and energies, but the trade-off is that you lose some non-volatility. And this may be okay, right? If you're trying to replace DRAM, that may be okay. And the device size also reduces that way. So this is also interesting to examine going forward. Okay, so we did a bunch of studies very similar to what we've done for phase change memory. And if you actually replace, again, capacity equivalent, we assume this is perhaps optimistic for this technology, right? We assume that if you do ISO capacity, if you replace DRAM with phase change memory, you get much better results. The performance loss is within 10% of DRAM. And you still need to architect, meaning you still need to handle writes nicely. But you don't need to do as many things as we've done for PCM for this technology. And you get significant energy savings compared to DRAM also, because the read energy is not a problem, right, in these devices, and write energy is not as bad as phase change memory. So in the end, you get significant energy savings. But always take these results with a grain of salt. These are for emerging technologies. But I believe that energy benefits of STT-MRAM are going to be significant once this technology becomes more viable in terms of capacity. Okay, if you're interested, you can read the paper for more details. And that's the paper. Okay, any questions? Otherwise, we'll keep going, because we still have half an hour. No questions? Is this fascinating? I think so too. I think there are other technologies lurking around, so if you're interested in technology, you may want to look into some new technologies. Okay, so these results are promising, but I think in the short run, or maybe forever, it's going to be difficult to replace DRAM with some other technology. The DRAM is actually quite good. That's one of the realizations that we've come to also. It's a very nice technology in terms of the latency and energy that it offers at the capacities that it has. Clearly, you can get higher capacity, but it comes at a cost of very high latencies or very high energies. So as a result, I think this is a more viable solution going forward, at least in the shorter term. And you've seen this picture before. Basically, you have a hybrid memory technology. or multiple memory technologies. We put them together, and these technologies are hopefully different in the greens they provide and different in the reds they provide, so that you can take advantage of this heterogeneity. Right? Of course, now you're adding more complexity into the system. You need to somehow manage that complexity. You need to basically design the hardware and the software to manage the data allocation and movement across these different technologies, such that you can achieve the greens as much as possible while avoiding the reds as much as possible. So this comes at complexity, but I think scalable, this is another, I think, fundamental trade-off. If you want to scale a system, you'll need to add more complexity into the system. Well, ideally, we would like to minimize that complexity, but there's no other way around it. And in this case, you're going to exploit heterogeneity, and heterogeneity by nature adds more complexity into the system. If you can scale homogeneously, that's great, but clearly, as you push the homogeneity to the limits, you'll have to go into heterogeneity at some point. And we'll talk about heterogeneity even more in later lectures. Okay, so we're going to talk about these hybrid memory systems now. And basically the challenge over here is how do you provide the best of multiple metrics with multiple memory technologies. And this is not a new thing in a sense, right? If you look at a flash device, it has a DRAM in it. Essentially, by nature, it's a hybrid technology. You need to manage the DRAM to provide better endurance to the flash. Right? And they've been doing, flash memories have been doing that, SSDs have been doing that for decades before this. But now you have to do it at the latencies that are at the main memory level. So you need to be a lot more careful. Okay, so I think this is the challenge and opportunity. Okay, so there are many issues over here, which we're not going to cover all of them, right? So how do you use these different technologies? Do you use one of them as a cache, or do you use both of them as main memory? Are both of them visible to the programming language, right? One of them may be invisible to the programming language. It may be used as a cache that's managed by hardware or software. We're going to see that a lot. But there's another usage, which is really having two different memory spaces, right? One is DRAM space, one is phase change memory space, and expose that to the programmer, and the programmer does the data allocation and movement. I think that's a nightmare for the programmer in the end. But if the programmer knows what they're doing, exposing some of that could be useful also. I don't think you want all of the management to be done that way. But maybe for programmers who really know what they're doing with their data, you may want to provide interfaces such that they can allocate data in DRAM versus phase change memory. That could be useful for programmers who know what they're doing with their data. So we're going to see a lot of the usage in terms of cache. Granularity of data movement and management. Is it fine grain or coarse grain? At some point you need to move data between phase change memory and DRAM and vice versa. Do you do it at 4 kilobyte page granularity, larger granularity, or smaller granularity, cache block granularity? This actually has implications in terms of performance. And also mapping, right? Because if your granularity is very large, that's good for the mapping structures. Meaning you need to keep less metadata to keep track of your number of blocks, because you have a smaller number of blocks by nature. But if your granularity is small, let's say 64 bytes or even 8 bytes, smaller than a cache block, now you have a problem because you need to keep track of every single 8-byte block that you have in your main memory, and your metadata becomes huge. But your bandwidth waste becomes much lower, right? Whenever you're moving data, it's just 8 bytes. So that could be very quick. So there are fundamental trade-offs here between fine and coarse granularity, data movement, and management. And we will see briefly. Who does the management is important. Is the hardware going to move the data? Is it going to be software that's going to move the data? Is it going to be hardware-software cooperative? You have to have some hardware support, no question about that, right? Clearly, if you don't have the path between phase change memory and DRAM in your memory controller, you're not going to be able to do this. Well, you could do it, I guess, by migrating threads and migrating data across machines even, but that's not very efficient. So in the end, I think hardware support is going to be essential for this, because the speed of this device is so fast that you cannot do the management of software. When to migrate the data, that's important. Which data is frequently used, what data to migrate. And also, I think this becomes interesting once you have very large caches. So if your DRAM is, let's say, I don't know, 16 gigabytes already, and if you use the cache for a 2 terabyte phase change memory, you need to manage this huge cache. And 16 gigabyte cache, if you have, let's say, 64 byte blocks, you have a lot of blocks in that cache, right? It's 2 to the 34 divided by 2 to the 6. That's 2 to the 28 blocks. Your cache tag store size becomes huge, right? And what do you do with that cache tag store? Do you put it in your memory controller? 2 to the 28 entries in your cache tag store, that's a lot, right? If each entry is, let's say, 4 bytes, that's 2 to the 30 bytes in the end. What is 2 to the 30? That's 1 gigabyte, right? You put 1 gigabyte of SRAM tag store in your memory controller? I don't think so. You might as well use the memory over there, right? 1 gigabyte cache itself, as opposed to using a tag store for some other cache. Okay, so this actually becomes really interesting. And there are other issues that we may go into. Okay, so let's look at the one option, which is using DRAM as a cache for phase change memory in a hybrid memory system. In this case, PCM is main memory, and DRAM caches the memory rows or blocks at some granularity. And the benefits are you have reduced latency on DRAM cache hits, and you also get write filtering, meaning writes are written directly to DRAM, and if you're writing to a block many, many times, DRAM absorbs those writes. And you reduce the number of writes that you do to PCM, which is really good for performance, energy, as well as endurance. Right? So this way you can reduce the writes. It's very similar to how DRAM is used in an SSD that manages a flash. And memory controller hardware manages the DRAM cache. This eliminates the system software overhead. You could do some of the management in system software, but it's a lot of overhead if you just do it purely in system software. So we're going to assume memory controller hardware does the management. So there are 3 issues over here. One is what data should be placed in DRAM versus kept in phase change memory. The other is what is the granularity of data movement. And the last one is how do you design a low-cost hardware managed DRAM cache. So we're going to see several examples of this. So I'm going to give you examples of 2 idea directions. One is locality-aware data placement, and the other is how do you do cheap tag stores and dynamic granularity. But before we go into it, this is actually perhaps one of the first papers that looked at a hybrid memory system that consists of DRAM and phase change memory. Essentially, this was published concurrently with our paper, and I said this is the more optimistic paper. The goal is to achieve the best of both DRAM and PCM. And the idea is to minimize the amount of DRAM without sacrificing performance and endurance. It's a different way of looking at it. You don't want to get rid of DRAM, but you want to minimize the amount of DRAM such that you get the benefits of both technologies. So in this case, DRAM is used as a cache to tolerate phase change memory and write bandwidth, as we've discussed. Right here, you get also high bandwidth. That's one of the other benefits of using DRAM as a buffer. And PCM is used as main memory to provide large capacity at good cost and power. And you can see the system design over here. There's also another write buffer that's included over here, so DRAM is a buffer to buffer the writes, but there's also a write queue that buffers the writes that go out of the DRAM into the PCM, and they need to be stored somewhere, clearly, so that you can actually reduce the number of writes even more to phase change memory, because writes are a problem, clearly. Okay, so this paper introduces multiple techniques. Basically, these are write filtering techniques. One is called lazy write, and the idea is very simple. Whenever you, I think the management in this paper is at the page granularity, so it's 4 kilobytes. That's the assumption over here. Whenever you get a page, 4 kilobytes, you bring it directly into the DRAM. You don't write it into PCM. That reduces some writes, clearly. If you have a hybrid memory, you can do this, right? If you have just PCM, you're stuck. You cannot do it. You could do partial writes. This is very similar to what we discussed earlier. Only dirty lines from DRAM page are written back. But you could also reduce the granularity of the partial writes, make it word granularity or bit granularity. And this paper also used a technique called page bypass. It basically, whenever you evict a page from DRAM, you check whether the page is going to be used. You consult a predictor. And if the predictor says you're not going to use this page, you don't write it to PCM. That reduces the writes even more. You write it, well, actually you don't need to write it anywhere if the page is not dirty. If the page is dirty, you need to write it back to flash, of course. Okay, so these techniques actually get rid of a lot of the writes, but they're still not enough, as we will see later on. So this paper takes a more system-level approach because its assumption is that the capacity, we're going to look at a capacity of phase change memory that's much larger than DRAM. So we're going to compare an 8 gigabyte DRAM to a 32 gigabyte PCM system. That's the assumption. Basically, the assumption is that phase change memory is 4x denser and 4x slower. Reads and writes, there's no distinction in this work. I think writes are actually more problematic than 4x we assume that it's more like 12x, right? And I believe that an order of magnitude is a good ballpark today. I don't think writes are going to be as close to 4x going into the future in PCM unless someone solves this very high temperature problem. So the results are therefore a little bit more optimistic here because of that. But also some of the benefits, as you will see, are going to come from the capacity benefits of main memory. So there's some simulation that looks at overall system, and the assumption is that page size is 4 kilobytes. But let's take a look at the results. This is performance results. We're going to see the energy results in a little bit. This is the performance normalized to an 8 gigabyte DRAM system. Performance meaning execution time. So lower is better in this case. So that's 8 gigabyte DRAM. If you actually look at 32 gigabyte PCM, clearly the performance is much better, right? Because you're gaining a lot of performance from the capacity. Now, what's happening is your memory is much bigger, so you're not accessing your SSD as much because of demand paging. That's the big benefit that you're getting. But if you look at a 32 gigabyte DRAM, that's even better. So clearly, there's still a difference between. So this is the comparison that we have done basically. 30 gigabyte PCM versus 30 equivalent DRAM. So that's 30 gigabyte DRAM is even better. So the question is, can you get close to the performance of the 30 gigabyte PCM, 30 gigabyte DRAM? And if you actually add a 1 gigabyte DRAM to the 30 gigabyte PCM system, you get somewhat close. But even this is not as good as 30 gigabyte DRAM, as you can see, even though you have 33 gigabytes total. But that's the benefit of a hybrid memory. It gets you closer to an almost equivalent size DRAM memory. Does that sound good? So I like this study because it actually takes into account the capacity benefits. Basically, you're getting rid of some page faults in this case. Okay, so essentially the PCM DRAM hybrid performs similarly to a similar size DRAM, but you also get significant energy savings with that. So this is, let's look at energy over here. This is 8 gigabyte DRAM, and this is hybrid over here, and this is 32 gigabyte DRAM. So if you look at energy, you can see that the energy benefits are much higher over here. So the energy benefits are clearly coming from the lack of refresh, the lack of idle power, and partly because the writes are actually much lower energy in this system over here. So these are also very optimistic, I think. It's not clear if these energy benefits are going to be available soon, but maybe longer into the future. Well, and the average lifetime in this work is 9.7 years. Again, there's no guarantees, but because of the write filtering techniques that are employed, you get around 9.7 years. The unfortunate part is no guarantees, of course, right? You really want some guarantees in this case. You may actually have an adversarial access pattern that essentially fools all of your write filtering techniques. And people actually looked at that later on. How do you actually prevent those adversarial access patterns that get rid of a lot of your memory by exploiting this endurance problem? Okay, so if you're interested, this is actually a very good paper to read also. It was published by IBM, Moin Qureshi, and I'd recommend reading it as well in companion to our work. It was published actually right next to each other. Our paper was the first to be presented at ISCA, and this paper was the next. And there's another paper on PCM that we're not going to talk about right now. Okay, so let's actually generalize the problem a little bit. The problem is even more general than PCM DRAM. It's really about hybrid memory in the end, right? And you can actually study this problem theoretically as well, which is really interesting, but we're not going to do that. Essentially, the problem is data placement in hybrid memory. You have two types of memories. They have, and this is really simplifying the problem, as you can see, right? One memory is fast and small, and the other memory is large and slow. You can even ignore the endurance problem here. So the question is, where do you place a page, assuming the page granularity? Which memory do we place each page in to maximize system performance? Okay, I already said the same thing. And also, I think there's, whenever you do this, you run into, again, a load balancing problem. Whenever you have multiple channels, and if you want to, for example, take advantage of memory A, it's fast and small, you overload it, let's say. Now you have a channel over here that's idle. So even though this memory may be slow, you may want to not put everything over here, right? Because you have a good channel bandwidth to this memory. So load balance is very important. This is Zürich Airport again, right? Keep that in mind. Whenever I see that airport, this sort of issues come to my mind, basically. And if you ignore that, you actually lose performance, right? Because you halve your bandwidth in the system. Even though this latency may be very good, if you halve your bandwidth, you may not be able to recover the performance loss that you induce. Okay, on top of this, page migrations have performance and energy overhead, essentially. So we're going to talk about a couple of works. Basically, the idea is to understand your data access patterns and guide the data placement in main memory. So the observation in this work is, if you have streaming accesses, if you're streaming through memory, you can make those as fast in PCM as in DRAM. Basically, PCM is a row buffer, and you can stream through the row buffer, right? Or you can design your PCM such that the streaming bandwidth is great. Whereas if you have random accesses, these are much faster in DRAM, right? Because DRAM is much faster in terms of read latency. Streaming happens through the row buffer, and row buffer is essentially an SRAM in either of those technologies. That's the idea. Whereas random access is really exercising the technology itself. Actually, if you're doing streaming, many technologies are very good. Like if you have a tape, streaming bandwidth that you get out of the tape is really great. Latency is very long, but once you start getting the first data, you'll get the next data, next data, next data in a streaming fashion relatively quickly. So your bandwidth is very good in many technologies. And you can design many technologies to provide very high bandwidth for streaming, even tape. In fact, all you're doing is streaming out of memory. You may not want to invest your money in these technologies that provide good random access latencies, right? Because you don't care. What you care about is your streaming bandwidth. Like if you're doing streaming bandwidth in terms of video and you can tolerate how fast you can get your video out, this only read-only. This is a read-only operation. And you can store all of your videos on a tape. And you can just basically wait for the video to be streamed in. And your performance will be as good as you have DRAM streaming video into your device. So it's good to understand your accesses. Where a technology, an expensive technology really matters is in random accesses. Meaning you're not streaming nicely, you're accessing this location and then this location. There DRAM is much faster, basically. So essentially you can think of this as row conflicts, right? Whenever you have row conflicts, DRAM is much faster. Whenever you get row buffer hits, it doesn't matter what technology you use because the row buffer can be similar in all of the technologies. Right? That's the idea. So this paper exploits that observation. It basically says once you have this observation, it's very simple. You can place random access data with some reuse in DRAM and streaming data in PCM. And that leads to a good hybrid memory management mechanism. Okay, I already said this, but essentially row buffers exist in both DRAM and PCM. As a result, row hit latency is similar in DRAM and PCM, whereas row miss latency is small in DRAM but large in PCM. And by exploiting this, we can develop a technique that places data in DRAM that is likely to miss in the row buffer, that has low row buffer locality, because miss penalty is small in DRAM, and that is reused many times. That way you can cache only the data that's worth the movement cost, data movement cost between PCM and DRAM space. So if you're not going to reuse a data in DRAM, you might as well just access it in PCM and not bring it into DRAM, right? Because DRAM space is valuable. It's not a lot. And you're using it as a cache. If caching is not going to provide benefits in your data, just get it from PCM. That's the idea. Okay, so if you do this, how do you do this? It's written in the paper. It basically has a hardware-based mechanism to detect what accesses are streaming and what accesses are random. You could potentially do it at the higher levels, right? Compiler can mark the access as streaming accesses versus random access. That's also possible to do. Or the programmer can indicate hints as to which accesses are random, which accesses are streaming. That's also possible to do. We did it in hardware. I think hardware is a good place to also discover these. But if you have higher level information, you can feed it also into the hardware. And if you do this, these are the results. Again, this is a pessimistic comparison, right? The comparison is you have 16 gigabyte PCM performance, 16 gigabyte DRAM performance, and there's a huge gap between them. And if you actually use this technique, you're almost halfway. Not halfway, actually. And also, of course, there's other stuff that goes on in this technique that takes into account writes, but I didn't talk about that. You can read the paper for more details. You need to basically ensure writes are treated nicely so that you don't cause endurance problems. But as you can see, the performance benefits of hybrid memory is better, but it's still not as close to DRAM. especially when you overstrain your system. We actually wanted to overstrain the system and have a lot of workloads that are accessing memory. And if your intensity to hybrid memory increases, then you have actually problems in terms of sustaining performance that's going to be closer to DRAM. So this is why I think it's going to be very hard to beat DRAM, even with hybrid memories, as you can see over here. But of course, you can argue that this is always a pessimistic comparison. Maybe you should be comparing to 64 gigabyte PCM over here, right? I somehow don't like doing that, in the sense that, yes, at some point you'll reach that, but this is a very fundamental way of trying to get a system very close to an equivalent or capacity equivalent system. Okay, so if you're interested, you can read this paper. Let me give you some other ideas very quickly related to this. So this is not the state-of-the-art work anymore. There are a bunch of works that are done in hybrid memory. There are actually a lot of ideas in terms of how to manage hybrid memories. I'll give you a couple over here. Essentially, they're all based on heuristics. Even this paper that I'm going to talk about is based on heuristics. But as you start considering more and more information, you do better, essentially, even with heuristics. Essentially, if you look at the robot for locality-aware management, it doesn't capture overall system performance impact. If you want to place a page to DRAM versus PCM, ideally you would like to capture what would be the performance impact of doing the placement into DRAM versus PCM, or what would be the performance impact of caching this block inside DRAM as opposed to not caching the block inside DRAM. Wouldn't it be nice if you had a performance model that can give you this prediction, so that you can decide based on this performance model? And that was our goal in this work. And I think this is actually going to be very important going into the future. How do you actually get a good performance model that gives you an indication of where you should place the data? Okay. Essentially, I think one example of what to include in this performance model is memory level parallelism. We discussed this before, but if you have concurrent memory requests from the same application, and when a page is accessed, that increases your memory level parallelism. And it affects how much page migration helps perform. So I'm going to give you an example. It's very similar to parallelism over batch scheduling at a very different level. So basically, let's say you have this memory B, and you have this memory A. Memory A is faster than memory B. So you have requests to page 1, and after you migrate that page 1 to memory A, you save some cycles, clearly. That's great. And that application latency reduces if this is the only page that the application is accessing at the same time, concurrently. So migrating one page reduces stall time by some amount. But let's assume that the application needs 2 different pages to make progress. Right? You have request to page 2 and page 3. They're both in slow memory. Now if you happen to migrate only one of those pages to fast memory, you don't gain any performance. This is the curse of memory level parallelism in a sense, right? You need both of the data elements to proceed, and you made one of them faster, but the other is slower, so your performance impact is 0 in the end. That's why you need to be very careful, I think. You really need to migrate 2 pages to reduce the stall time by the same amount over here. That's the idea. That's why I think it's important to understand how your decisions of migration actually help performance. Migrating one page really alone doesn't help in this case. So page migration decisions, for example, need to consider this, the stall time impact of the migration. So essentially, this work provides a generalized mechanism, generalized within the constraints of what we were able to imagine at that time, right? I think, again, a machine learning mechanism would do much better than this. The goal is to directly estimate the performance benefit of migrating a page between any 2 types of main memory, and to place only the performance critical data in the fast memory. So performance critical means the data that will impact reduce the execution time the most if you migrated it to the fast memory. And there's a mechanism for this. It's heuristic based. I'm not going to go into the details, but it turns out it actually works with any hybrid memory, meaning it doesn't require. Essentially, what you really need to consider is latency and bandwidth parameters of the memory. And the key idea is for each page, there's a metric that's called utility, and we use a bunch of characteristics to calculate the estimated marginal utility of migrating a page from one memory to the other memory in the system. And utility is defined as performance impact in this case. And the system migrates only the pages with the highest marginal utility. In other words, the pages that improve the system performance the most when they're migrated. And of course, to be able to do that, you need to estimate utility somehow. And this paper develops a performance model to estimate that utility. And it migrates only pages whose utility exceeds some migration threshold. And it periodically adjusts the migration threshold because application behavior changes. So clearly, you can see another heuristic-based approach here. It's an insightful heuristic-based approach, but maybe machines will do better. Okay, so how do you actually estimate the utility? You need to estimate how much an application stall time will reduce if you migrate this page. So there's a performance model for that. And also, that's not enough, right? Because you may be running multiple applications in the system, and if you migrate this page, this application's performance will improve by some amount, but the application may not be that sensitive in the overall system, right? How much does the improvement of a single application's performance increase the overall system's performance? You need to estimate that also. So there's some utility metric, and in this case, this is the high level. And then you need to estimate the delta stall time, and you need to estimate the sensitivity. And the paper actually has heuristics to estimate those. Okay, if you do all of this, let's take a look at what the performance improvement is. Essentially, in the most intensive workloads, which are probably the more interesting ones, most intensive means all of the workloads are quite intensive. You're really accessing memory a lot. The performance improvements are about 14% compared to what we discussed earlier, the row buffer locality-aware management. So I believe this is actually currently the state of the art in terms of hybrid memory management, in terms of hardware-based mechanisms. This doesn't change the software. All of this is done in hardware. Okay. And actually, this is the beauty of simulation, I think. Once you have a good simulation environment, you can change the latencies, and you can see how good your mechanism is. And in this case, this is a slow memory latency multiplier, meaning how slow is the slow memory compared to the fast memory. For example, here, reads are 3x slower and writes are 3x slower. It's not just reads and writes. Activates are 3x slower and writes are 3x slower, right? Here, activates are 7.5x slower and writes are 20x slower. So you can actually see the spectrum. And as you can see in all cases, the mechanism that we described actually improves performance well. But you can also see something nice over here, because these are comparable to each other. As your latencies of slow memory increases in terms of multiplier, your performance also reduces, right? So there's a reduction in performance. And some mechanisms are less graceful in terms of reduction in performance, and some mechanisms are more graceful. But I'm not going to go into that. Basically, your hybrid memory management mechanism can tolerate the latencies better if it's a good mechanism. That's the idea. Okay, I'm running slower than I expected. I'm using slow memory, I guess. Or slow course, I don't know. But maybe this is a good place to stop, because I have this nice picture over here. Basically, this is a huge, it's a big challenge and opportunity right now to enable an emerging technology to augment DRAM. Read places, I think, a very hard problem right now. So augmenting is an easier problem. How do you actually manage hybrid memories to augment? So this is a good place to stop. I think next week we're going to talk about GPUs and prefetching. And then after that we may get back to some more hybrid memory later on. Okay, have a good weekend and see you next week.